University of Waterloo and Perimeter Institute. The title is on the screen, not homology and coherent sheaves on Coulomb branches. Ben, please.
All right, thanks so much for the invitation. This talk is at least supposedly about homological not invariants. So let me say some tiny amount about topology. We aren't going to need very much, but we will need a little bit. So I often like to think about not invariants in terms of the category of tangles. In this case, I should have revised my slides a little bit and forgot to add this. I should have said oriented tangles. That's the O-tang. So this isn't a category where the objects are choosing a set of points on a line, and I'm calling them plus or minus, and that's whether when the oriented tangle joins them, it's oriented up or oriented down. So the morphisms between these, we sort of think of these sequences of signs as like co-oriented submanifolds of R, and morphisms between them are tangles. So embedded one manifolds inside a plane times an interval, which join one at the top and one at the bottom, matching orientations and doing some tangly stuff in the middle. And one of the nice things about these is they're a category. You can compose them by gluing and sort of smoothing out to make a submanifold. So it's kind of awful to write this in words. It's much better to draw the picture. So each object is one of these horizontal slices. So for example, here I have one thing in my sequence and it's a plus, which means I want a tangle that joins it with one strand and upward orientation. And you see here I have sort of more things. Here I have plus, plus, minus, and here I have minus, plus, plus. And I just draw one manifolds going between them, and this is all happening inside a three-dimensional space. So my one manifolds can cross either from, in a positive way or a negative way. And note in particular here that links are thus morphisms in this category from the empty set to the empty set. And it's often helpful to think about link invariants as really being representations of this category. So yeah, there's a sort of natural approach to trying to construct an oriented not invariant, which is to define a representation of this category of tangles. Monoidal functor, tangles have a monoidal structure from putting two tangles next to each other like this. Into the category of vector spaces with usual monoidal structure under under tensor product. So what such a functor requires is, well, I should send the sequence with one plus to some vector space. And the sequence with one minus has to go to some other vector space. And it's very tempting to say V dual, but that's not quite right. It's actually that the two ways you can orient cups and caps give you a vector space which is dual to V in two different ways. And this whole story about like quantum traces, etc., is that it's not dual the left way, it's the same way that it's dual in the right way. A map corresponding to crossing, here I'm only looking at oriented upwards, and there have to be a bunch of compatibilities between these maps, which I'm not even gonna try to write out, but one important one is that these crossings induce a representation of the braid group on V to the tensor n for all n. All right, so a prime example of this is that for any finite dimensional representation of the quantum group associated to a simple finite dimensional Lie algebra, we can define a representation of O-tang, this is defined by Reshetikhin-Turaev, sending plus to that representation. And all of the maps corresponding to tangles are constructed in terms of objects in the representation theory of the quantum group, in particular, the crossing coming from the R matrix. All right, and this gives us an invariant corresponding to each link, which is actually valued in Laurent polynomials.
Sorry, Ben, you understand UQ of G as algebra over rational functions, or Q is fixed? I'm a bit confused in formulation of the theorem.
So hopefully I haven't done something dumb and screwed this up. I mean, I'm being a bit lazy here about like needing to add in fractional powers of Q and that sort of thing.
Okay, so you work with divided powers. Okay, good.
Yeah, sure. So yeah, I should.
So it's a little bit less than just vector space over rationals. It's smaller. It's okay, good. Mm-hmm.
Yeah, I mean, certainly you need a Q, and I mean, since I'm just looking for sort of the value of these invariants, it's fine to consider Q generic, which I can represent by saying it's a vector space over rational functions in Q. But you're right, the R matrix involves taking fractional powers of Q, that sort of thing. So I'm being a little slippery here. I might actually need Q raised to a fractional power. Anyways, this does give me a Laurent polynomial valued invariant of the link, which again is sort of, I have this representation of my category. I think of a link as a morphism from the empty set to the empty set. That gives me a morphism under the representation. That gives me a scalar, and that scalar is my polynomial. And it's because of some extra structure that it's not a rational function. It's actually a Laurent polynomial. All right, the most famous example of this that you're most likely to have heard of is the Jones polynomial, but there are many others. So the Jones polynomial is what happens when you put in the simplest representation of a simple quantum group you can think of, the defining representation of UQSL2. So there's a whole other zoo of these coming from other groups and other representations. And if you prefer physics, you can say a bunch of stuff about Wilson operators and Chern-Simons theory if you want to. This is sort of, at least should have been the inspiration for this. Not sure exactly how all of those things lined up in terms of ideas floating around. All right, so the idea of homological knots is that you kind of upgrade this story. So before this was I had a sequence of labels and I sent that to a vector space. Now I have a set of labels and I want to send that to a category. And before, whenever I had a tangle, I would send that to a map between the corresponding vector spaces. Now I want to send that to a functor between the categories. And if you can define such a thing that satisfies all the right compatibilities, then you'll assign to each knot a vector space. And maybe that vector space has some extra structure like a grading or a double grading, which is typically what happens. And you can get back these polynomial knot invariants by taking a graded Euler characteristic. All right. Now, I would rather somehow the really right way to do this would be to say, oh, actually, there's a two-category structure on tangles. So I can define morphisms between tangles by looking at cobordisms between them. And there is a lovely talk I wish I could be giving where I explain all of that and then tell you how that maps into some two category. At the moment, that's sort of beyond our technology. I don't know how to do that. Maybe someday we will figure it out, but so it's beyond my powers and the powers of anyone I know of at the moment. So we just have to be kind of satisfied with, I have my sort of sequence of points, that gets sent to a category. I have my tangle, that gets sent to a functor between the corresponding categories.
Sorry, what would that give you, that two categorical enhancement? Something like if you have two links that are coordinate, you would have universal relations between them or something?
Well, so what this would tell you, and there are sort of hints of this going on, for example, in Havanov homology, that there is some functoriality with respect to cobordisms. And so then what you would get, right, is that whenever you have a cobordism, you get a map between the homologies, right? That's sort of part of the point of upgrading a number to a homology, is that you can start talking about functoriality, right? I'm kind of stealing this example from Havanov, or this way of phrasing it from Havanov, but, why is it good to upgrade Euler characteristic to homology? Because you can't have a map between two manifolds and have a map between their Euler characteristic and like ask, is that injective or something, right? But you can do that with their homologies. And I mean, there have been serious theorems proven using the functoriality of Havanov homology with respect to cobordism, right? There's a proof of the unknotting number of torus knots using the functoriality of Havanov homology. And it's exactly like, if you have an unknotting of a torus knot, you can think of that as a cobordism, and it would have to do this thing to the Havanov homology. And, oh, well, that would be impossible if you could unknot the torus knot in fewer steps than this.
Awesome. Thanks.
Yeah, of course. So yeah, there definitely are hints that this is going on, and some cases where we can prove a version of this, but it's very hard in general. So it's sort of an interesting perspective, but a difficult one. So over the past, and I caught this right before the talk, but I didn't have time to change it. I wrote part, but I should have said past. 15 years, we've seen this kind of this big explosion of different ways of thinking about non-homologies. So kind of the kickoff to this was Havanov's construction of Havanov homology, but that sort of generated an enormous amount of activity in the area using lots of different tools. So some people use parabolic category O, or this work of Cautis and Kamnitzer using coherent sheaves on Grassmannians, work of Kefelek and Rose using sort of, and also Mackay, Stosich, and Vaz preceding that, using sort of combinatorial, like cobordism and foam categories, adding in relations. Havanov and Rosansky using circle bimodules and matrix factorizations, this old Seigel-Smith story involving Fukaya categories, and lots of interesting stuff in physics in dimension 6, 5, 4, and 3. So lots of different kind of ingredients going into this. And somehow there was this explosion of interest in doing this. I made my own contribution by trying to give a kind of instruction where you could define one for any representation of any quantum group by defining a sort of combinatorial algebra associated to your choice of sign sequence. I'm cheating a little bit here. This really should be like a tensor product of representations, but it's actually kind of good to think of it as this combinatorial thing. A sign sequence that gives us an algebra T sigma. Here I'm just sort of drawing the picture, but this guy will come back, which is why I'm mentioning it. And you look at the derived category of these. So I was saying you want to assign a category to a list of signs. So this is the way you do it. You define an algebra and you say, look at representations of that category. And every tangle gives me a bimodule between the algebras. And tensoring with that bimodule gives me the functor. And for very small, single crossing, single cup and cap, it's a pretty simple bimodule. But then to compose, you have to do a very complicated derived tensor product.
Ben, may I ask you a general question to your long list of these developments? All those people, I mean, they kind of define the whatever categorification actually based on the idea that knot is a closure of a braid. So they were looking for the braid group action somewhere, maybe by functors. it's different from Chern-Simons, where you don't have to kind of to look for the braid group action. You construct something directly for the node.
I mean, actually, relatively few of these. I mean, there's the sort of Zirkel bimodule story where you actually have to use a braid closure. Most of these other ones don't. It really is you assign something to any tangle, or at least sort of, yeah. So I don't know if I have a good answer. I mean, I'll say something in a moment about sort of how these all relate to each other. But I mean, actually sort of, I think one often ends up getting a bit misled if you try to do constructions where you take a braid and try to close it up. Like one thing you might kind of be tempted to do here is to say, oh, attached to a braid, I have a functor from a category to another category. If I can close that braid up, the two categories will be the same. You know, what I should be doing is taking Hochschild homology of that bimodule. And that's actually wrong. That probably gets you annular not homology. So ones that really depend on sort of how you're sitting on the annulus. And you have to sort of, to get a genuine non-invariant, you have to not do that. Never use Hochschild homology, just always use the functors that are attached to braids and to tangles. So I mean, yeah, I don't know, we can talk about that afterwards. All right, and I don't want to get kind of too deep into this, but I am going to bring back the relations of these algebras later. So I just want to say, you know, somehow the way these algebras work is they're defined by some diagrams modulo some local relations. These are the kind of local relations you have. But it's always sort of, if you could do some isotopy to simplify your diagram, well, either it's true right on the nose or there's some funny correction that comes out. You know, you have to multiply by a dot somewhere or something. So if you write out the full list of relations, it looks pretty long, but it's not really that bad once you kind of get used to it. All right, so, you know, somehow there was this burst of everybody was using their kind of pet object of interest to construct a knot homology, and it kind of seemed like, oh, wow, we have all these different knot homologies. And then actually it sort of turned out that the differences between these were really very superficial. And you actually keep getting the same knot invariants. You know, this is hard to make as a blanket statement because there are a few things like even Ivanov homology and odd Ivanov homology, but sort of the whole crew of these invariants that people defined, it then later turned out were all the same, provably so. And I think this is maybe not as well known a fact as it should have been, because somehow like everybody's really excited, and then this fact about them all being the same was kind of proven after the excitement had died down a little bit, and it was proven in a slightly complicated way by a bunch of different people over a bunch of different papers. I'm not sure the news ever got out.
Surely the physical construction must have been the same. There must have been some physical conjecture before the theorems that they were all proven to be the same. Is that accurate?
That's a good question. I mean, there were also different constructions of things in physics that don't obviously have anything to do with each other. And I mean, so the way that kind of the biggest swath of these were proven to be equivalent was basically to realize that all of them came from skew-how duality. That sort of all of them were actually constructed inside the Ivanov-Lauda-Ruquier categorification of a type A Lie algebra, which you can use to construct intertwiners between type A representations using skew-how duality.
Yeah, but maybe, I don't know, it's rather philosophical discussion, but still, like, if you, for example, do geometric representation theory, you construct geometrical representations which were known long before, like, and so it doesn't make this geometric representation theory is trivial. I mean, it's
Oh, sure. Sure.
Testing kind of a playground for different mathematicians and physicists, and they just use knot theory to test whatever duality or construction they. So it doesn't mean that all these 6 or how many lines on your previous slide that they kind of were non-interesting. So
I mean, I'm here giving this talk, aren't I? I didn't give up on this area and completely move on to do other things because I agree. Like, sorry, but I was in the middle of a slightly orthogonal thought, which is I don't think physicists have a really good explanation of where this Ivanov-Lauder-Ruquier 2 category comes from. So I mean, I'm perfectly willing to think that there is some physical construction that kind of all of these were some version of, but I don't think that's really the story we see at the moment. Okay, great. So as I said, you could say it's very disappointing that a bunch of these invariants turned out to be the same, but you could also say, oh, it's really exciting that we did these things that look totally different in all these different categories, and yet there's something actually connecting them together. And so I mean, I think I'm just kind of restating Jan's point that, you know, knot homology built out of a category is really kind of an excuse to dig into the structure of this category. And if that knot homology is the same as some other one, well, this is probably telling you something interesting about the relationship between your new category and some other thing out there. And it's sort of interesting to compare those, and the knot homology is kind of a motivation to do so. So my excuse here is that there's some recent work of Aganagic, which was about sort of construction of one of these categorified knot invariants, where kind of the category assigned to a sign sequence is the category of coherent sheaves on a particular variety. And unfortunately, you know, explaining all the constructions of this variety could be like a talk all its own. It'd probably be a pretty interesting talk. But the sort of 3 faces of this variety which are important is it appears in the affine Grassmannian. It basically describes the structure. By the way, are my neighbor's power tools getting too loud? I have my window.
No, that's okay. Fine.
I can't. It's sometimes hard to tell when things carry over to the mic, but it sounds kind of loud for me. Anyways, so one manifestation of this variety is you look in the affine Grassmannian, and I'm only looking at type ADE, so it's a little silly to say the Langland's dual, but it really is kind of right to say the Langland's dual. You look at 1 ger lambda, and this lambda depends on your sign sequence, and look at the sort of singularity of that at the trivial coset, and you take a resolution of that. You can also write it as a space of G-monopoles on R3 with specific singularities, which come from this sign sequence. I could say a bunch of stuff about Bogomolny equations and this kind of stuff. But for me, actually, the important realization of it is it's a resolved Coulomb branch for a quiver gauge theory. So I'll say a little bit about what Coulomb branches are, but the point is they're interesting algebraic varieties which you construct out of the data of a representation of a reductive group. And here I take the reductive group and representation that Nakajima uses to construct the Nakajima quiver variety.
Then just kind of to put a note in my head, so you consider the dominant weight and the other weight is, or co-weight, whatever, it's trivial, yeah? T in the power
Yeah.
0. Yeah.
Since I want the not invariant, I might as well use the 0 weight space.
Okay. Mm-hmm.
So somehow the way to think about this is, for each one of these sequences, I have, some tensor product of representations. Okay, and Nakajima tells me, associated to the 0 weight space of this tensor product of representations, well, there's an interesting variety, which he constructs as a hyperkähler quotient of, sort of built out of the quiver. And the thing you should do is look at the 3D gauge theory corresponding to that representation and group. So the 3D gauge theory, whose Higgs branch is that Nakajima quiver variety, and look at its Coulomb branch instead. So this is, in these fancy terms, the 3D dual, or sometimes I'll say a symplectic dual of that Nakajima quiver variety. So another one of these things I could spend a whole talk talking about is there's a sort of idea of three-dimensional duality or symplectic duality or S-duality of symplectic singularities, which is supposed to take in one symplectic singularity and spit out an interesting one which is dual to it in some very complicated way, but still has some tie back to the original thing. And Nakajima tells me a variety constructing to this weight space. I take the dual one. All right, so before things get too crazy, let me just say, what's my main result? My main result is this variety, the Coulomb branch that Aganagic is using. So she's using coherent sheaves on a resolution of singularities of this variety. I instead am looking at a non-commutative resolution of the same variety. So a non-commutative algebra whose representations behave like coherent sheaves on a resolution of this variety. This is going to be an algebra like the one I had before, all the same local relations, but instead of being drawn in a plane, they're drawn on a cylinder.
So should we know in which sense it is a non-commutative resolution?
I think you should take the definition that I said. So it's a non-commutative Crepin resolution in the sense of Vanderburg.
If you think that I read this 200 pages of Vandenberg, so
no, it's not 200 pages. But I mean, somehow for purposes of the talk, I think the correct definition is it's a non-commutative algebra equipped with a functor to coherent sheaves on this affine variety that behaves homologically like push forward of coherent sheaves from a Crepin resolution. So, somehow I'm happy to have a more detailed discussion with you about it afterwards, but I think for the purposes of this talk, that's all we really need to know. In fact, another way to think about it is it's a non-commutative algebra whose module category is derived equivalent to coherent sheaves on this algebra. So I sort of like this language of non-commutative resolutions because somehow this algebra exists all on its own without reference to any particular choice of Crepin resolution in the usual sense of algebraic geometry. But it's also true that if you choose a Crepin resolution, then you get an equivalence of derived categories of coherent.
So may I think about this theorem like that you have some explicitly constructed algebra like generators and relations, because I believe this KLRV, W, excuse me, it kind of means that generators and relations, blah, blah, blah. And then it's modules over it are equivalent in the derived sense to
Yeah, I mean, I was going to say this later, but what's actually happening here is on the X sigma, that's the resolved guy. On here, there's a tilting generator, a vector bundle that has trivial higher X.
it's
And generates the derived category, and endomorphisms of this tilting generator is A.
Okay.
But the point is, somehow like this theorem is true for all possible Crepin resolutions of this singularity. So it's sort of nice to make a statement about A that doesn't depend on choosing an explicit Crepin resolution.
So the really non-trivial part is computational, yeah, that you can write down it's in terms of generators and relations.
Yeah.
Mm-hmm.
Irina, did you?
Yeah, hi Ben. I also had a question, but you said that it behaves like the categorific, so cohomologically behaves like categorific Crepin resolution. So it is a statement that is beyond just simple category equivalence that you have here, that dB of a mod is equivalent to dB of coherent sheaves on the resolution. So is there some kind of Mackay correspondence? So what do you mean by it behaves like category?
Oh, I mean, yeah, I think we're kind of going deeper down this rabbit hole. But I mean, Vandenberg has a definition of a non-commutative Crepin resolution, which is, like you have a reflexive sheaf on the affine variety, and your algebra is endomorphisms of that reflexive sheaf, and it's the important thing is that you have the singular algebraic variety, and you detect that from the fact that its representation category is infinite homological dimension. And you find sort of a bigger category that contains those coherent sheaves and which has finite global dimension. And I mean, there is like a bit more going on there, but that's sort of the important point. Being smooth is having finite global dimension. And so this is something that behaves like it's smooth because it has finite global dimension.
Okay, thank you.
Mm-hmm. And so, this functor from A modules is there's a particular idempotent such that EAE is functions on this affine variety, right? And so the functor is hit in A module with this idempotent. So it's nothing extremely fancy, which is just that this tilting bundle is the structure sheaf plus some other stuff. You can arrange for the tilting bundle to have that structure. All right. Okay, so using this equivalence, we can interpret what the construction of Aganagic's not homology. So Aganagic says, okay, take coherent sheaves on these varieties, apply these functors to them, which, I don't find extremely illuminating how these functors are. I mean, it was interesting to see them because I saw them and I was like, oh, I know on the other side what those are going to be. But, somehow they're a bit abstract and hard to work with. And if you take them through this derived equivalence, they become explicit bimodules exactly like I have here. So kind of everything can be defined purely using sort of algebra. There's you can kind of cook all of the physics and geometry out of it and just write everything explicitly in terms of algebra. And so we can define a kind of purely algebraic construction that matches Aganagic's and is basically the cylindrical version of this story I was doing before. And of course, you might ask, especially if you're Irina, well, doesn't that mean that you should actually get tangles, not just in a plane acting, but tangles on your cylinder, so your tangle could like wrap around the cylinder? And the answer is absolutely yes. So you get some invariant knot of knots drawn in the plane, but knots drawn on a cylinder. Presumably these are the same as annular knot invariants people already know, but I haven't actually checked this. I mean, it's one of these results where I mean, it must be, but I haven't actually confirmed that. All right. Okay, so that's the end of the introduction. 35 minutes into the talk, but that's all right. So let me try to explain a little bit what the heck is going on here. So what are these Coulomb branches? So Coulomb branch, that's a more general term in physics. I mean specifically for 3D n equals 4 supersymmetric gauge theories for a gauge group G and a representation N. So I, for a long time, had been interested in the story about symplectic singularities. And so physicists had been telling me that Coulomb branches were an important part of this, but they could never really tell me what Coulomb branches are. They would say, well, if you compute the Coulomb branch classically, then you take the carton of your Lie algebra, you take its Langland's dual, you take the cotangent bundles of that. They didn't say those words, but that was what they meant. And then you mod out by the action of Lie, which, you know, fair enough, but there's something a little fishy going on here. In particular, the representation doesn't appear anywhere. And they said, oh, well, that's the classical calculation. No, you want the quantum Coulomb branch. So there are some quantum corrections. And then they, you know, they would say some stuff about the hypercalorimetric changing, and I could never figure out what the heck was going on. And so luckily, Braverman, Finkelberg, and Nakajima did that for me. They figured out how to make sense of what these quantum corrections are. And kind of, that's another thing that could be its own whole talk. So let me just say sort of the hint here is that if your representation is trivial, then this Coulomb branch is actually spec of the homology of the affine Grassmannian equivariant for the Taylor series group. And basically they figured out, oh, okay, so I know this fact. How do I now incorporate my representation? And what they were doing, if you phrase it all in physics terms, is they were computing the local operators in the A twist of this theory by looking at a trivial line operator and computing endomorphisms of that. And the less I try to say about that, the better, I think. So I'm going to be interested in the case of quiver gauge theory. So that means my G is a product of GLNs corresponding to the nodes of my quiver, and my N are matrix algebras corresponding to maps along my quiver. So, you know, I have a quiver, I have arrows in it. The gauge groups are associated to the nodes, and then the components of N are, well, this one corresponds to arrows, and then the other one corresponds to these guys correspond to some framing vertices, which shows up in Nakajima's story as well. All right, and then we do something which, you know, I've been thinking about quiver representations for a long time, and I've never thought to do this, which is you look at the Taylor series and Laurent series versions of everything. And so I'm always going to use sans serif letters for the Taylor series and OI-FRAC for the Laurent series. So you can take the sort of Taylor series versions of these. So if I just take an N mod G, that would be some moduli space of representations of this quiver. So when I make everything sans serif, that means I do everything over the Taylor series. And so I'm getting representations of the quiver over the Taylor series, which I can also think of as maps of the spectrum of Taylor series into this quotient. And similarly, I can do that over Laurent series. I can look at the moduli space of representations of the quiver with coefficients of the Laurent series as well. And bizarrely enough, I do some sort of standard calculations in geometric representation theory, but using these spaces instead of, you know, things like the Springer representation. These are some sort of infinite dimensional analogs of like the Springer resolution. So I have a natural map from the Laurent series bit, sorry, the Taylor series version to the Laurent series version, which is just think of a representation of coefficients in Taylor series as a representation of coefficients in Laurent series. And I can take the fiber product of two copies of the Taylor series going down to the Laurent series. So I say this is this sort of standard Springer representation type story. So that's the moduli space of quiver representations with Laurent series coefficients with two choices of lattices inside them. This is like the Steinberg, which is, like, elements of your Lie algebra and two Borels that can take them. It's the same kind of thing. So by the sort of usual convolution, I get that the homology of this fiber product has an algebra structure. And as I said before, you can think of this as maps of the disk, speck of Taylor series, or the punctured disk into this quotient. So I can think of an element of the fiber product as I have a representation on the punctured guy, this representation of the Laurent series, and I choose two lattices inside it that tell me how to extend over the disk in two different ways. And this picture of extending over the disk in two different ways, this is called a raviolo. So this product, you can think of this as sort of up above, we have the double raviolo, and we have the maps. This is like when you're cooking ravioli and two of them get stuck together. So you have a map that's pull off the blue one, you have a map that's pull off the red one, and you have a map that's like take the guy in the middle and mix up the fillings. And you pull back, take wedge, take cup product, and then push forward. That's the product. And amazingly, this gives you a commutative algebra, and the 3D Coulomb branch is its spectrum. I know this is like kind of a wild story. Let me just pause for questions. You guys are all there.
So you said that if something was equal to 0, it's just cohomology of equivariant homology, Borel-Moore probably, of the affine Grassmannian, yeah? And so if it's commutative, it's algebra of functions on something.
Yeah.
And what is it? Something?
That's the 3D Coulomb branch. That's the definition.
No. In this simplest case.
Oh, in this case, I mean, that something is, there are a couple of different ways to describe it. It's the universal centralizer in Lie algebra. It's this constant slice. It's the phase space of the Toda system. Yeah, so I think the n equals 0 version of this is, I think, Bezrukavnikov, Finkelberg, and Mirkovich. I think that's right. And they phrased everything in terms of the universal centralizer in Lie algebra. That's spec of the homology of the affine Grassmannian. The reason you get something commutative is basically the Ekman-Hilton argument that this picture with the double raviolo, you can think of that as really like you have a disk and you puncture it twice, and you can move the two things around each other. So that's why you get a commutative algebra. Unfortunately, like you can't actually do that in algebraic geometry, right? You can't take spec of the Taylor series and puncture it in two different places and move the two punctures around each other. But that's kind of morally why the argument works. You have to say some fancier stuff about factorization to do it properly in algebraic geometry.
So here in this slide, that the algebra structure on A on the Borel-Moore homology, that's the product is a convolution. But in the earlier slides, you have the equivariance homology. So what is the multiplication structure on that?
Here, I mean, this is just, so, right, the affine Grassmannian is the Laurent series mod the Taylor series, right? So I can think of, wait, I should just get a new page because this is going to be a mess. I try to write this.
Oh, I see. So that will be the double cosets.
Yeah, if I think about the double cosets, so that equivariant homology, I can think of that as the double cosets. And this double cosets, that is secretly point mod the Taylor series, point mod the Taylor series, fiber product over point mod the Laurent series. This is a general fact that you can think of the double cosets, like you can always think of.
So in this case, in this product, the A is not necessarily commutative.
No, it really is something special about the fact that you're taking a group and taking its points over the Taylor series and its points.
This is the algebra.
So yeah, it involves the factorization property of the affine Grassmannian. So yeah, one variation I like to do on this is to mod out by the Iwahori instead of the Taylor series group. And then you don't get something commutative. You get a non-commutative algebra.
Yes, thank you.
Okay, great. So that's the Coulomb branch. Now, why are these interesting? Well, because you actually get a lot of interesting varieties this way. You can get the nil cone of GLM. That's one of my favorites. That comes out of this quiver theory, or generally Slotovy slices in type A. And another one that's very interesting is the symmetric power of C2 mod ZL. And people like to think about the symplectic resolution of this, which is the Hilbert scheme on C2 mod ZL resolved. And those of you who know these varieties might know that these are all Nakajima quiver varieties, but they're Nakajima quiver varieties for potentially different quivers in different dimension vectors. So the sort of quiver variety in Coulomb branch, again, this is a 3D mirror symmetry. So if you have a type A or affine type A quiver theory, it's S-dual, it's another type A or affine type A theory, but for a different quiver in a different dimension vector.
But when I'm a bit confused, so for those Nakajima quiver varieties, so there is no stability, so they're singular, but you can choose an appropriate stability condition and resolve. Now,
Yes.
you said that on the Coulomb branch, you have a similar story.
Yes.
They're singular, but you mentioned something like Crepant resolution. I mean, they can be resolved at least probably sometimes.
Yes.
Does those kind of resolutions on both Coulomb and Higgs side, they are related somehow?
Yeah, I mean, so in these particular cases, all of the Crepant resolutions can be constructed both by the Nakajima GIT quotient construction, and on the Coulomb branch side, there's a construction due to Braverman, Finkelberg, and Nakajima of partial resolutions of Coulomb branches, which in this case give you actual symplectic resolutions.
Okay.
Again, I'm happy to explain. It's not sort of that complicated a story, but I think I want to. I'm running out of time, so I better keep going. All right. So, okay, I had promised that these were going to be related to these KLRW algebras, and I'm running out of time, so I don't know if I'm going to be able to say a huge amount about this. But let me just say, right, you remember I said before, well, actually, I kind of like to use the Iwahori, and how that manifests in terms of thinking about actual quiver representations is instead of a quiver representation with a compatible lattice, you want to think about a quiver representation with a compatible affine flat. So I'm taking m copies of Laurent series. So there's a notion in here of an affine flag, which is sort of, you take the notion of a lattice and then you kind of choose a complete flag in the vector space between the lattice and the lattice times t. So it's, that should have a -1. So I have a sequence of lattices, fk, that satisfy that they're nested like this, and that when I multiply by the variable, I shift my whole picture by k minus m. So if I only look at these guys, which are congruent to a fixed residue mod m, m is the number of copies of Laurent series I have, I just get a lattice, the same lattice times t, the same lattice times t squared, the same lattice times t cubed, etc., on forever in all directions. And then the other residues give me another sequence of lattices that sit between these guys. So these are good because flag varieties are better than Grassmannians. Grassmannians, they're nice, but they're sometimes hard to work with. And there's a lot of things that are easier with it when you think about them in terms of flag varieties instead. So let me not get kind of too deep into the details here because I don't have much time. But you sort of think through, okay, what does it mean for quiver representation over the Laurent polynomials to have a compatible flag? Well, you sort of have to say at each step when you go from one flag to the next one, you're going to be changing over one vertex in your quiver, and you have to say, well, which vertex is that you're changing? And so that ends up giving you a periodic word in the nodes of the quiver. And then actually there's a red copy of the nodes of the quiver, which have to do with, I had my sort of vector spaces sitting on my vertices in my quiver, and then I had these framing ones. And so I take the standard lattice inside the framing ones, and I also have to think about how do I interact with the standard lattice on the framing vertices. Okay, so for each one of these kind of periodic sequences, I get a space of quiver representations over the Laurent polynomials with a compatible flag where I hit these vertices in this sequence. So I can think about that as a moduli space, the moduli space of such choices. And that gives me a D module on the space of, so there's a map, which is forget the flag and only remember the representation of the Laurent polynomials. That gives me a D module on the space of Laurent polynomial representations. This Y, remember this is quiver representations over the Laurent polynomials. There's a bunch of physics words for this, where this is a half BPS vortex line operator compatible with the A twist of the theory, which when you try to actually make that a mathematically precise thing, you say, oh, actually, that's a D module on this space of quiver representations, moduli space of quiver representations over Laurent polynomials, or the loop space of the moduli of quiver representations. So since I now have a bunch of these guys, instead of just considering this one convolution algebra of choose a lattice, I can say, oh, think about choosing a flag of this type and then a flag of some other type. I can take those fiber products and that whole thing picks up an algebra structure, again, using convolution product. Okay. And that convolution structure has a presentation by this sort of cylindrical KLRW diagrams with exactly the same local relations as before.
Ben, do you understand correctly that if you do the same thing in finite dimensions without affine periodic flags, you get something which is not on the cylinder but on the plane?
Exactly. It's so if you do this in just normal finite dimensional vector spaces, you get this algebra I drew before. That's these diagrams in the plane. And exactly what happens is sort of all the local calculations about what happens when you adjust things in an affine flag, they're all the same as the local calculations in the finite flag. It's just sort of the context in which you're doing them has changed, right? So they all have to do with, okay, forget one step of your flag, think about like, ways of choosing a new one. So it's all like literally exactly the same computations. But it's all now kind of in this different context. And that's expressed algebraically as it's the same local relations, but on a different set of diagrams. So now my diagrams are on the cylinder, and it's because I needed to have a periodic word. So now each slice of my cylinder, right, gives me a periodic word that corresponds to compatible, type of flag that could be compatible with quiver representations of the Laurent polynomials. So there's a weird mix of like, it's kind of mind-bending, but if you understand the finite story, it's no harder. It's all the same stuff as the finite story. You're just putting it in a different context. Okay, yeah, I'm running out of time. So you can then prove that this guy is convolution algebra. So it contains inside it, the Coulomb branch is one example. And you can prove that it's basically what happens when you take all the black strands and pinch them together at the top and pinch them together at the bottom. So just choosing one lattice. And so you can prove that this guy, this KLRW algebra, the cylindrical one, gives you a non-commutative. Here I wrote symplectic because crepant and symplectic are the same for symplectic singularities, non-commutative symplectic resolution of M. And I'm almost out of time, so let me try to wrap this up. Let me just say the proof of this, at least at the moment, the proof I know kind of goes through this quantization and characteristic P story of Kalyedin. Hopefully someday that won't be necessary, but it kind of makes things easier, and it's a nice observation. But actually, this isn't just any old non-commutative resolution, it's the one that comes out of this Kalyedin construction of characteristic P. And I don't know how much I want to say about that. You get a quantization by just including an extra C star equivariance, the C star that acts by weight 1 on your parameter or rotates your disk. Yeah, I think I'll just skip by this stuff. So by sort of doing this story in characteristic P, you can sort of follow this cookbook of Kalyedin, and you get a vector bundle. And I should just say, somehow the way you find this is by diagonalizing a commutative subalgebra of the quantization. So right, this gets you a tilting generator. So you can actually find there's always on any resolution, there's a tilting generator whose endomorphisms are this cylindrical KLR algebra. And that's actually how you prove that it's a non-commutative resolution. You can take the bimodules I had before for tangles in the plane, and you can just upgrade them to tangles in the cylinder. Again, you use all the same local relations, but now you're drawing everything on a cylinder instead of in a plane. That's the only change. And this gives you, in particular, a finite link homology by you don't wrap around the cylinder, you just stay without wrapping around. And this defines new non-homology, but it's not really new, it's old. It's the same as this older non-homology work I had done in the plane, and it's also the same as this Aganagic story. So it shows that this stuff Aganagic is doing, it's constructing the same non-invariants as my older construction, and thus the same as Rosansky, the same as sort of all of these other different constructions in type N. All right, I think I'll finish there. Thanks for your time.
Yeah, thank you very much. It's, the end of the talk was a bit compressed. So, questions?
I was just trying to end on time.
No, I mean you don't have to. I mean, it's people in this seminar. People can go over the time, and some of them really did. Okay. Now, concerning your last theorem, how you compare? I mean, your construction with others, especially with Mina.
So, I mean, the construction, so I'll answer the easier part first. The comparison with my own construction is, I mean, it's actually pretty simple. It's basically like, I prove that, you know, at least certain functors between the categories that I had in my original construction can be essentially cylindricalized, kind of, you can fold around the two sides and glue them in the back in a way that commutes with composition. And so basically, if you take the bimodules from my old construction and cylindricalize them, you get the bimodules in this new construction. And so everything's compatible with composition, and you get out my old non-invariants. And the comparison with Mina, I mean, the sort of right, like, I don't think it's extremely hard, but it requires understanding Mina's paper, which I don't do perfectly. But you know, the sort of important point is that the braiding part of this tangle action is this the wall crossing functors from, you know, earlier work of Bezrukavnikov, Coulomb, Loset, etc. And so I actually proved in an earlier paper that these kind of combinatorial bimodules match the wall crossing. So that takes care of that part of it. And actually the sort of part that had bothered me the longest, I sort of for a long time had known that, you know, some version of this must be true. And part of why I didn't kind of write out the details and sort it all out was I didn't have a good explanation of, like, where do the cups and caps come from? So the really valuable thing I learned from Mina's paper is a kind of more natural description of the cups and caps, where she's thinking about sort of central charge on, you know, her category of coherent sheaves. And actually, you can interpret that cohomologically, or sorry, not combinatorially, for representations of this algebra. So this is one of these things that, like, it sounds slightly insane when you say it, but I think it's actually a pretty cool idea. If you have a representation of this algebra, and let's say a finite dimensional one, then kind of for each place you put the black dots on the circle, you get an item. So let me actually just add a page. So, you know, I have my circle, and I have red dots which are in a fixed position, and black dots which I'm allowing to move around. And for each positioning of my black dots, I get an idempotent in my algebra, which is just take this circle and extend it up through the cylinder, right? So now I turn this into a cylindrical picture with both my red and black lines being straight. So this is an idempotent. You know, let me call this EX, where X is like the position of the black dots. And well, for any module, I can look at the statistic, which is the dimension of EX times that module. And then I integrate that over all the different places I can put X in this S1, which, like, when I realized you could write things this way, I was like, this is insane. But this actually is like this sort of central charge function that Mina is thinking about. So I proved, actually, this is building on some work of Rina's, this function, this gives me a real variation of stability conditions.
So stability conditions on what?
On the category of, well, you could either say coherent sheaves or representations of this algebra. Right, so the point is, you know, somehow
Coherent sheaves, I sort of understand this geometry because it's kind of pretty simple, like as for representations of this algebra.
So what you should think of this, you know, so I mean, I think if you look at the original real variation of stability paper, right, they sort of say like, oh, your sort of real stability condition should be given by, like, you know, you have this characteristic P story and you're looking at the dimension of the representation in characteristic P. And this integral is actually a continuous version of that. So somehow computing the dimension of the representation in characteristic P is replacing this integral with like counting lattice points weighted by these dimensions instead of taking an integral. So like this integral is like the limit as P gets very large and you divide by the right power.
Then do I remember correctly that for Minas, it's sort of, she also has some filtration by the behavior of the central charge near.
Yeah, right. So that's part of the story of real variation of stability. That
but
the wall crossing functor, when you hit a wall, is a perverse equivalence where the like layers of the perversity are what your order of vanishing as you hit the wall is. So in this picture, hitting a wall means moving two of these red points together. So this function varies depending on where you put the red points. And so what's happening here is like you're bringing the red points together and you have your order of vanishing as those two red points come together is like how many black strands are trapped between those two red guys. So if you have a module where you only get a non-zero image of the idempotent if you have a bunch of strands in the middle between your two reds that are colliding, then that means that the central charge, this integral, vanishes to that order as those 2 points collide. So this order vanishing, it has purely algebraic interpretation. And yeah, the story of Minas is basically like the cup and cap should come from when 2 points that correspond to dual representations collide, you look at the lowest, the sort of biggest order of vanishing subcategory, and that should be the same as the category where you just remove those 2 points. And again, I had actually basically already proved this in my older paper, and I just didn't realize that this was like a fact that I wanted to prove. Like somehow I already had all the machinery to do this in my older paper, but I hadn't noticed that this was an interpretation of what was going on. So this sort of explains why the particular random looking bimodule I write down for the cup and the cap is the right thing, but I already knew that bimodule.
Yeah, that's cool, but I do not. So yeah, that's interesting. Yeah, so it's combinatorial. Yeah, I mean, I don't know. I mean, kind of long ago when we did with Maxim that Donaldson-Thomas story, we thought about compactification of the moduli space of stability structures. more or less kind of in a similar way by sort of filtrations coming from the behavior of the central charge near the walls. Yeah, and there is some operatic structure which actually we did not work out, but you know, it's sort of, there is a basic operatic structure when it's called Fulton-McPherson operand, when you have a collection of maybe points, or even this little disk operand in topological version. But it's more difficult to compactify it if it's little disk, but for Fulton-McPherson, it's like stable analog of stable curves. Your points collide, form new components, and so that's algebraic structure, which in Mina case, it was a structure of conformal blocks when some points on the configuration space collide. Yes, so it's all about stability condition, but I haven't thought about purely combinatorial, so it's really cool. It's really something. You said that you had it in your old paper, in some of your old paper, or you already.
Well, you know, what I mean is I had kind of done all the calculations, right? I mean, in my old paper, I had to like define a functor that corresponded to cups and caps and prove that it had certain properties.
And when you say old, what paper?
Oh, I mean, my paper, not invariance and higher representation theory. So the one where I constructed the usual, you know, categorifications of all the Reshetikhin-Turaev guys. Yeah. I mean, actually, I think there's a link in my slides. Let's see. Will this actually work? Oh, no, I guess not. I don't know if this is a problem with GoodNotes or something. I don't know if that link actually works in.
No, it doesn't. I already tried. So.
Okay, shoot. Well, it worked in the original PDF, but I guess when I imported it into GoodNotes to be able to write on it, it ruined the link.
Okay. Good. Okay, so I occupied the whole discussion. Okay, other questions, please?
I'm sure nobody's upset with you.
Maybe.
So that's the.
Okay. You put in the chat the reference. Okay.
But you know, I mean, I think there's a certain amount of like, if you read that paper, you won't see the structure here because it wasn't how I was thinking about things. So it's sort of, you know, basically what I'm saying is, you know, thinking about in terms of these perverse equivalences and this filtration, kind of put those earlier calculations in a different context that actually kind of matched what Mina was doing.
Yeah, she gave a talk here last year, but it was kind of course, completely different.
Yes, it's a very, very
language
different.
And sort of more understandable, but less. More understandable in the sense that it's basically categories of equivariance sheaves and something and stability and blah, 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 книжник замолодчиков, quantum differential.
Right. Well, I mean, sort of.
It's sort of, but it wasn't clear how much of that could be made precise. It's yeah, so, but it's cool. And you say that the only way you kind of understand this quantization story, it's through finite characteristic. Yeah.
Well, I mean, there's this funny thing, right? That like, for example, like Mina said, like Mina's construction, at least the way she describes the braid representation, she says it's the same as this characteristic P1 that Bezrukavnikov and Coulomb are using, right? But at least that was sort of my understanding of it. So, somehow like I have to bring in the characteristic P stuff to like compare with what they're doing. And also it's the easiest way to prove that it's actually a tilting generator.
Mm-hmm. Yeah, that's I understand, yeah. Okay, so people, it's the last chance to ask Ben a question.
Well, I've always not asked the question. Yeah.
Okay, go ahead.
It's always a ridiculous question. Ben. So here I was using by the homological homology, you're using the loop rule. That's the one single variable. And you have this algebra, which is a symmetrical knots. So what happens if you have, this is a one-dimensional on the curves. You have two-dimensional, you have two variables locally. And do you get something like a torus knots? Or did anybody ever even try to think that way?
Yeah, I don't know. I mean, I'm sure there's some interesting physical story there, right? This is like, basically what you're trying to do is like upgrade into a four-dimensional theory from the three-dimensional one I'm talking about. So, I mean, the short answer is no, I don't know anything about that story.
And from physics, I have no clue, but mathematically, if you have one variable, I want to go with two variables or even more variables.
Yeah, I mean, there's sort of, yeah, I think the short answer is no, I have no idea.
I know this is a ridiculous question.
I mean, it's not ridiculous, right? Like, no, and you can ask, like, what about elliptic stuff here? Like, right? So you have this Coulomb branch. I was taking homology of it, but you could also take K theory, and you could also take elliptic cohomology of it, right? And I'm sort of not sure what to say, kind of what interesting things you can say about those, right? Like you can take these kind of diagrams and deform the relations so they become the K theory relations or the elliptic cohomology relations. I don't know like what that buys you, why you would do that. I mean, to me, that's kind of the direction I would try to take that question is like, like your second loop, I would say, oh no, don't put the loop there, put it in the K theory.
That's right.
And then maybe we'll actually be able to do something. And there is sort of some interesting stuff about like, I mentioned that you can get the universal enveloping algebra of GLN by doing this Coulomb branch story and quantizing it in homology. Well, you can get the quantum group by doing that in K theory, right? So there's sort of, there are kind of interesting things going on in this K theory, and I just like, but I don't actually sort of know what to say about it.
I don't know if you noticed, Joyce had a series of a paper on giving some kind of a stack conditions on which to get a vertex algebra structure, and if the stack is formulated correctly, so which is also using a Borel-Moore homology multiplication as what you were using in the case. So I don't know how this will be related. So.
Yeah, I don't know. I mean, there is like, there's an interesting vertex algebra stories here that I don't really understand. I'm sort of trying to get one of my students to work on it, where basically like, you've gotten this algebra by doing some topological twist so that sort of everything is happening in the disk and it's happening kind of topologically in the disk. But you can do some kind of less severe twist away kind of less of your theory and get a theory that's holomorphic on the disk instead, and get some vertex algebra coming out instead of an E3 algebra. But yeah, that's still a fairly mysterious story to me.
Actually, since you mentioned vertex
Thank you, Ben.
algebras, yeah, your half colleague David, he had this construction of the vertex algebra at the corner.
Mhm.
Yeah, and as a special case when kind of 2 out of 3 indices are equal to 0 or something like that, you have just moduli space, the vertex algebra, this W algebra for GLN acting on the cohomology of the moduli space of framed sheaves
Mhm.
on CP2, this AGT story. But this moduli space, it's sort of a special case of this very special case of the Coulomb branch. I'm just curious whether anybody thought about this generalization of BFN, which kind of handles not just a single a formal disk and the punctured, whatever, this raviola which you mentioned, but intersection of raviolas. Because what David did, it looks like in general it's a collection, like 3 copies of CP2. On each of them there is its own life, which probably is described by BFN, but they intersect kind of non-trivially in the ambient space. And I was curious how to generalize. Is it possible to have? Yeah.
No, sorry, I don't.
Yeah. It's of course it's kind of this crazy question, but yeah. All right. So, are there any questions after Dongzhu? Who's supposed to be the last one? Okay, if not, thank you very much, Ben, for very interesting and inspiring talk. Thank you. And so then this is it for today. Thank you.